Hello everyone, welcome to Layman's AI, a channel dedicated to simplifying AI content. In today's video, we're going to talk about RAG models. How do you take RAG models to productions? We'll talk about fundamental concepts, brief introduction about RAG models, and mostly we'll talk about the reference architecture that you could follow when you take things to production. What are the challenges that you're going to see, and how do you mitigate them? That's all we'll do. So stay tuned. My name is Sunny, and I'm going to talk about how do you take RAG solution to production. Now, in RAG solution, let's understand what is the primary problem with LLMs in general. So, when you work with LLMs, the primary issues that you will encounter is around knowledge cutoff, right? Because a pre-trained LLM is expensive to train, you will always have a knowledge cutoff, and your model doesn't know about future data, right? So that's why you need to do what is called a fine tuning process on your custom task. But that may not be relevant for many use cases where you would just be able to inject the data into the context and get the answer, provided you have the access to the data, right? And there's all other concerns around data privacy where people don't want to fine tune models on hosted models, hosted LLMs for concerns, right? So these are the reasons why I know you cannot use a pre-trained LLM out of the box, but you have to build what is called a RAG. A RAG stands for Retrieval Augmented Generation. This is a model, an approach proposed by Facebook in 2020, and this has been very popular since then. And people have been trying to build a lot of customer facing bot solutions with this use case. So we'll deep dive out on this topic more, but let's first understand few fundamental concepts which you're going to encounter as we more discuss about this around vector database and embeddings. This is a very fundamental and central point of conversation. So let's understand what is an embedding. Now embeddings are very simple. In simple terms, they are numbers, numerical representation of text or any kind of data, not just text, images, audio, anything like that, right? So see, at the heart of LLMs are fundamental. What is an LLM actually? It's a deep neural network, right? There's a bunch of networks which are talking to each other to understand numbers, right? So they need numbers. LLMs need numbers, right? So you just can't feed any text into it, right? So embedding is basically a process by which you convert text into numbers or any kind of data into numbers. So, for example, I have this text, I am feeling great to learn about embeddings. I have to convert them into some kind of numbers which represent the semantic property of the text, right? What does it mean? It means that if two words are similar or co-occur or mean the same thing, the numbers associated with them will be closer, right? If they're antonyms, they'll be far off in that scale, right? So in simple terms, when I say embeddings, what I mean is I say an algorithm by which I can convert text or any kind of data into numbers such that the numbers retain the semantic property of the text, right? Usually this process is a deterministic process, which means every time you do embeddings using an algorithm, you should get the same numbers for the same text, right? Usually it should be. So, for example, this is a visualization of from the TensorFlow projector where you could take the word to back vectors and see how those projection looks like. There are multiple dimensions. So in simple terms, this is basically to tell you that when you project the numbers into that high dimensional space, the closer they are, they mean something similar, or there's a relationship between them, right? That's what it means, right? Now let's understand vector database. Now vector database is so central that it will come again and again when we talk about RAG. So what is a vector database? A vector database basically sorry, a vector database basically indexes and stores vectors. What is a vector? As I said, the embeddings that we generate are basically numbers. Those are vectors, and you store them. A vector database has the ability to store them and index them so that it can do efficient similarity search. So if you look at the normal traditional text based search where you take a text and then search in the database, it uses text matching algorithms, right? Partial match, complete match, things like that. In contrast to that, in a vector database you use what is called a vector search algorithm where the numbers are used to search, right? A vector database is also like a traditional database, so you should also expect capabilities around scale, how do you scale the database, how do you partition the database, do CRUD operations on database, and how do you maintain it. These are also very critical component of your vector database. uh, and you should follow what is called a hierarchical structure to store vectors in database. I will talk about this a little later in detail, but these are fundamental aspects of vector database that you should look for when you're choosing one, right? So what happens is when you get a new text or a query, you can use the vector database to kind of filter the zone where the vectors similar to that context will be, and find that that local area where those documents reside, so that you could use that for your prompt, right? So that's, in simple terms, a vector database. So let's understand what is the hierarchical structure that I was talking about. Okay, so let's take a simple example. If somebody is storing, let's say they have a large amount of documents that they have, and they store their documents like this in a folder, do you think it's going to be easy for for the same person to retrieve information when they need it? It's going to be pretty difficult for them, right? Instead, if you organize your data in a more structured approach, where you could use different layers of organization structure. Now, for example, I use category and then time based slice, right? So depends on depends on the use case that you have. It depends on the way you, as you, if this was for you, you would probably organize it in the way you would look for things, right? So if it makes sense for you to put this by years, and then by quarter, and then within a quarter you put all the reports by categories, or let's say you have multiple product lines, you have multiple products, and then you could follow different ways to structure this. But fundamentally, as an end user, you're going to follow a structure which makes sense for you from a retrieval standpoint, right? When you want it, what would be a more easy way to get it, right? Keeping that in mind, you would organize this, right? This exact um, you know thinking process applies when you structure your data for RAG in your vector database. If you start dumping everything into an index, it's going to be hard time for the retriever to get the information. If you make things more organized, it's going to be way more useful. Okay, so that's a design principle you should be aware of when you're kind of organizing the structure, right? Now let's understand about RAG in general. What is the pipeline, right? So there is a user who comes with a query. So query is the text, for example. So we convert that um, to an embedding. So there's an algorithm by which we'll convert that into an embedding. So you have an embedding now for the query. So you can then use a search algorithm to search your vector database. Right now, this vector database has the embeddings of all the documents that was already there. So let's say you have a bunch of data repositories, a bunch of documents, and coming from multiple systems. You already have some kind of pipeline build which will split and create the chunks, and then do the embeddings and store the embeddings in the vector database. So your vector database is ready with all the embeddings, and it's always, this is an incrementally changing database, so new documents are coming, you're getting updated and inserted, right? So the user's query embeddings are searched, so you get what is called, so you filter the chunks that you're retrieving, maybe the top k the points that in the chunks that you're retrieving, and these chunks this become part of the prompt. So you take the query, the prompt design that you have built, and the context is from these chunks, right? You combine all of this three together in some template that you have designed, and then you send this to your LLM. This could be ChatGPT, your OpenAI models, GPT-4, Llama, whichever sorry, whichever LLM model you're using, right? And then, assuming that your prompt has the required information to answer the question, the response will be generated, and this response is what you'll present to the end user. So this is the overall structure of how a RAG model works, right? In this process, there are some fundamental tunable settings that you could think about when you're building this, which are important because they will influence the overall quality of the solution. So let's touch upon those points, right? What are those tunable settings, right? One is chunk size, overlap, and tokenization. So when you're building the vector database, you have to find out the right chunk size that makes sense for your use case, right? Too small or too large is not going to be good. Something in between is good. This is something that you should empirically find out for use case. Now, today, as of today, there are some good practices, but this industry, this domain is so new that people are finding out new things. So in my opinion, it's always good to experiment this out and empirically find what works best for you. So what tokenizer to use, how much overlap should you have between your chunks, all of those things are tunable parameters you should look for. The vector search algorithm is the algorithm with which you are going to search vectors for similarity, right? There are multiple and many of them. This is also an area of active research, and you should always look for the algorithm that best fits your use case and gives you best results, right? So that's also something that you should experiment with. Metadata search is something very critical. So it's not just about the chunks that you're storing in the database. You also have a lot of metadata about the chunk itself. So where did it come from, who are the nearby content, at what time was it generated, who generated it? All of that. The use case, for your use case, all the metadata that makes sense is going to be useful, and you should model this in your database design, because if you're ignoring the metadata, then your search is going to be fairly weak and very slow also, right? So metadata search is also important, and you need to figure out what metadata makes sense for you. Some things like source of the data itself, where did it come from, and the time it was generated. These are some very crucial metadata that you should always consider having it, right? Pre-processing filters is basically, sometimes when you build this, when you're doing the retrieval part of your rag models, you have to put some pre-processing filters where you define what kind of filters you want to do before you get the retrieval process, right? This basically says, based on some logistic, based on some logic, you're saying how you want to decide what kind of filters to put on your query, right? The query that you run on the vector database, right? So those things also are, experimental part. You need to do that. There are post processing filters also, where once you get the results from your vector database, how do you, are you going to put some rules on which results to consider and which not to consider, right? For example, once you get the result, you may write some rules to say drop this result and include this, right? Those are also things that you need to be working on. Mind that sometimes, mind that this processing filters should be in a manner where they don't become slow, right? They are not working in a sequential manner, otherwise they can just slow down your entire pipeline. And the prompt design itself. So when you build the prompt design in which you're going to put this context and the original query and the question that you're asking, you need to experiment with the design well, so that you see which design of the prompt is working well for you, right? So these are something that you should look for. Now, let's say you've built all of this and you're going live. What are the challenges that you're going to encounter? So once you go live, there are some fundamental challenges that you're going to see. These are very common, and most people encounter this. So one is wrong response, right? Your users will complain that when they ask a question, the response that they get is factually incorrect, or even if it's correct, it doesn't make sense for the question, right? So you will see this feedback most of the time, and this is a very difficult problem to solve, and one of the most important problems that we have to address, right? The second problems are more around latency and cost. So because of your design, your architecture may not be scalable, or the way you are making the calls may not be scalable. That's why you'll see a very slow response in the entire pipeline, which impacts user experience, right? And cost is again something which is going to hit you, because in the initial design we do rough calculations on what is the prompt size, number of queries, number of users, blah blah blah, and you get some cost. But when you go live, you might see 2x 3x of that cost. So you need to be caring about how do you get that optimized. So in this session, we'll not talk more about latency and cost, but we'll talk more about the first part, because that is more from the design perspective. It's going to be very useful. um, so when you say wrong response, this fundamentally happening because of the two components that you have in your rag model. One is the retrieval component, and then the second is the generation component, right? The retrieval component is the first component, which is getting the results from your database, right? So if your retriever is bad, your generation is also going to be bad, irrespective of that, because your LLM can't find an answer if you don't give it in the context, right? So what are the things that you could go wrong in your retrieval? The first problem is low precision, which means that you have some irrelevant results in the context. So let's say you do top k, where k is 5. So you do a search and you retrieve the top 5 documents or chunks, right? Out of this, let's say 3 are relevant, but 2 are irrelevant chunks which are coming. So this corrupt that context, right? When you corrupt the context, your LLM might get confused and give you wrong results, right? So because of this low precision, where unnecessary results are coming into your retrieval process, they impact your you know the experience. The second is low recall, which means incomplete results, which means everything that was supposed to come did not come. So let's say, for you to build the context properly, you need five responses to be coming, but you only got three. You didn't get the two, right? Because you didn't get the two, your context was not complete, and hence the generation was weak, right? So precision is about getting corrupted data, unnecessary, irrelevant data. Recall is not getting the coverage, which is not giving the entire correct data that you look for, right? These are the two problems that you'll see, right? And third is the stale data problem, which is more of a pipeline issue, because your database doesn't have the latest data, because you have not written the pipeline well enough. That's why it doesn't have, and hence you are getting this problem, which is more than which is still a solvable problem, but you need to be aware that this can happen, right? On the generation part, you will see two big challenges. One is hallucination, which is the model, because of the way the data is presented to it, is either not confident about the context or the problem, hence it's hallucinates on its own, just generates an answer which is not correct. And the second is lost in the middle, which is like you have so much in the context that the actual information that is needed to solve the problem is somewhere hidden in the entire text, and it is tough for the LLM to actually find the correct answer, right? These are the challenges that you're going to see, and these are going to bombard your initial experience when you go live with your solution production, right? So we'll talk about a little bit on the reference architecture, and how you should architect the solution, so that most of such problems can be dealt with in a more practical, pragmatic approach, right? So let me talk about the reference architecture in terms of how could you build something for the entire pipeline, right? One is, so the first thing is your multiple source systems where your data resides. This could be documents or APIs or URLs from where the data is supposed to come. It could be a push based mechanism, or it could be a pull based mechanism. A pull based mechanism is where you write some kind of crawler which will go to your systems and get the data and periodically index it. And you could also have a push based system where some system automatically keep on pushing the data. You will actually have a mix of the two depending on the type of systems that you interact, right? So in your pipeline, you should have some kind of a asynchronous queue based layer. You can think of this something like an SNS or a pub sub, right? So what this does is, in an asynchronous way, it connects to your source system and gets the data that you're looking at, right? This system should get any kind of data and convert them into a message, right? A message is, you can think of that message as simple JSON, where you have a multiple key value pairs around the document. Like for example, let's say I'm getting a PDF file, where did I get that, which URL, what was it about, what was the title, who is the author, when did I get, all of these are key value pairs which would come part of the message, right? And the actual document goes into a blob storage. You could use blob storage like an S3 or something like that, right? You can store that data there, and the message is where the actual the message is basically the JSON which tells about the document itself. So you have this pipeline where your systems are sending, or you going and receiving that, and you're putting that in your message. Whenever there's a message in this, you should have worker nodes. These worker nodes are basically processing engine which will pick up a message from your queue and process that. It's important to organize these worker nodes in a parallel manner, so that there's they work in a stateless manner. They don't need to share state. Any kind of state that they have to share should be stored in a persistent store, like a database externally. By directly working with the queue based system, they kind of share the state of the message itself. So once they complete a message, they update the system saying that the message is completed, so that way other nodes don't process the same message, right? So this design is important, so that way you can scale your pipeline in which you are processing these messages from your system, right? Now, one important thing that you should do is, every worker node which is generating these chunks out of this document, every chunk that you generate, you could use a robust LLM, like for example GPT-4, to generate Q&A pairs, right? So for example, let's say I have the power of a PDF document, right? And I could use this to generate a Q&A pair by using ChatGPT. I could ask this to ChatGPT saying, hey, this is my paragraph, generate a bunch of questions which I could answer using this content, right? And ChatGPT will give you a bunch of questions. Now what happens with this is, this Q&A pairs are basically telling you that what kind of answers can be coming from that question, right? Sorry, what kind of answers can be coming from the question. So in that This data can become useful for you to do downstream numbers, right? When you are simulating various kind of parameters, you could use this data to see how good is your retrieval working, how good is your completion working, all of that, right? It's a good idea to store the Q&A pairs, which will help you in the downstream evaluation process, right? So this worker nodes will store all of the data, the chunk, the embeddings, the vectors, the metadata, all of that in the vector store. And in addition to this, you need a logging infrastructure, usually a document database, where you can store all the entire conversations that are happening on your bot. What was the user query? What was the response? What was the context? All of that. So that will help you do analysis when things don't go right, right? You can also incorporate feedback from your users when they like or dislike your answers. That will help you in your reinforcement learning in the next stage when you are actually evaluating how to make your solutions better. Let me quickly also touch upon a little bit on the evaluation methodology that you have to follow for this, right? Now, as you understand, in your RAG, there are two parts. One is the retriever, one is the generation, right? These two are independently working and you need to evaluate them independently, right? So for the retriever, you should look at precision recall. So every time there's a query, there's an embedding, and you search and you get some results, you let's say to top K, is the top K right? Are you getting the correct answer in this top K? Are you getting unnecessary answer? All of this is important. And remember, we talked about the Q&A pair, which we automatically generated during the indexing time. You could use those question answers already generated to automatically evaluate your retrieval, right? You could use the same questions from the from that Q&A and expect the same answer. If you don't get it, you know the ground truth, so you can evaluate how is your retrieval doing that. So precision recall are like two very important numbers that you should measure. If you're making those experimental settings that we talked about in the initial slide, if you change them, what is the impact on the retrieval? Is the retrieval rate increasing or not? You would be able to measure them. And I think it's very important that you build a mechanism by which you can automate the evaluation process for retrieval, because you will be doing retrieval very often than needed, right? And you cannot rely on humans to do it manually where they look into conversation. You have to build a diverse test data set which will be used for retrieval process evaluation, right? On the generation, a few things that you should look for is faithfulness and relevance of the answer. Faithfulness about how correct is the answer that you're looking at. Relevance is the answer relevant for the question, right? Something could be correct but it is not relevant for the question, right? Google also brought in this metric called sensibleness and specificity average, which was for the Mina bot. It's also a good way to look into whether the answers that your bots are giving in an open-ended conversation, whether they are relevant, sensible and specific to the question, right? So these are something that you should do when you're evaluating your RAG solution. And this is an iterative process, as we all know. Like most ML solution, this is an iterative process. But I will also stretch on the on the overall pipeline in terms of how you're going to evaluate this and make changes and make it scalable, right? This is a more advanced concept, but I think it makes sense for us to understand this. Is this whole idea of incorporating graphs into this ecosystem of RAG, right? um, Let me take a step back and let me talk about graph database in general, because this is something that has changed the relational database world, right? So when we used to store data in the relational database world, when we store data, uh, relational databases actually don't have relation as their first generation entity. Relationship is kind of second generation or secondary, achieved through joins and things like that. And that's why doing relationship based queries are very complex in a relational database actually, right? And that's the reason what has led to the birth of the graph database, right? What graph database do is relationship is native to them. And with this whole idea of nodes and edges, you can actually model a complicated thing, and with very easy to understand queries, you could actually do things which are, on the other hand, very complex to be done in a relational world, right? And that's what graph database has done, right? So I've dealt with many production grade deployments where we have shifted a lot of the search from the relational from a traversal perspective to a graph. The raw data still resides in the relational database, but the queries that are to deal with some kind of traversal. So for example, let's say if I have customers and products and what did they buy, given a customer, I want to find their products that they buy and what are the other customers who have bought similar products, and then recommend, something like a collaborative filtering. This query is very complicated when you write this in a graph, in a relational database. But when you write this in a graph database, it's pretty simple. If you model the data properly, it's very simple, right? And that's why graph databases have, are very useful whenever you have a large search problem. Every search engine or any large product platform, there's large, where there's a search problem, they'll have some kind of graph in between, right? I think the same thing is going to happen in the vector database space, where you're going to rely too much on the vector database to do a lot of search in terms of semantic vector search. But as you scale up, at some point of time, when you have this metadata, the metadata concept of time based slicing, and then using metadata to crawl and then find out where. So when you have a large graph, you know so if you model your vector database in a graph model, where you use a graph to store the nodes and the metadata, and then the chunks, in fact, your graph database will also allow you to store the embeddings, the vector embeddings in the nodes and the edges, so you can do a search there. But my personal preference is, I try to use something that works best for that use case. Most of the time I found a blend of these two things more useful. So you could use the database, vector database, for the embeddings, but the metadata and the traversal base of queries, the kind of traversal that you need to do, can be modeled into a graph, right? So this is important. I would suggest that if you're building a production grade RAG application, you may want to consider some component of, how do you, I think there's a requirement, there would be a requirement for you to incorporate some kind of graph in between for your knowledge graph. And your knowledge graph is your metadata on your, on your data that you have. And you use that as your first level search, so that you can get to a subgraph where your document reside, and then extend that with the vector database to kind of get you the relevant stuff, right? Now, on the vector database specifically, my suggestion is, go for a database that your people, your team, and your company and your organization has skill sets on that. Because just don't introduce a new vector database just because it is making news. Use something that, because when you vector databases are going to be, the database is, it's a database, so you will have challenges around scalability and maintainability. So it's going to be crucial on which database to use. If you already have skills in your company in a specific, look for that. Every relational database is coming up with a vector extension. So for example, PostgreSQL, which is the most widely used open source database, has already come up with PG Vector, which is an extension. And there are a lot of enterprise products that are built today, as of today, on this vector database extension, on open source databases like relational databases, right? So look for that, bring some graph components, and hopefully you will be able to take your graph solution. So before I wind up, one last thing that I want to talk about is, I hope this was useful for you, and I'll try to come up with something more, more stuff on this area. Um, so stay tuned, hit subscribe for getting notification. And just one last thing, if your data looks like this, if all your RAG data is dumped like this, then you're setting up for failure. So that's my warning. Don't do that. Pay a lot of attention on how do you want to organize this data, so that your search is well, and you're getting the right information. Thank you for your time. Bye bye.